In this segment, we're going to talk about so-called compressive summarization, or a summarization approach which extracts content but then also deletes parts of that content in order to focus better on the most important information. So to call back to one of our earlier examples, we talked about grabbing this fragment. A massive earthquake of magnitude 7.3 struck Iraq on Sunday. But notice that this is actually not a full sentence. The sentence goes kind of on and on and on, and we probably don't care about a lot of what happens in the rest of it. So we want to be able to pull out the sentence, but then also delete content from it. So the first approach we're going to think about is just using sort of syntactic cuts. Basically, having some rules over parse trees can tell us where we're allowed to delete content, and this can give us a little bit more flexibility during the extraction process to sort of shape our summary the way we want to. So for example, if we look at the parts for this sentence, we have these so-called adjuncts, this temporal adjunct on Sunday, and this location here, 103 kilometers, 64 miles, blah, blah, blah. And we are going to allow ourselves to delete those. So what this looks like is we say to the model, okay, you're allowed to extract this sentence, and then optionally you can delete these two nodes in the parse tree and everything else that comes underneath it. So if we deleted these two, we would be, not including on Sunday and 103 kilometers in the summary. All right, another example of what we could delete is with coordination. At least 6 people were killed and many others injured. We could delete this bit about many others being injured and just keep the first piece here. So some of the earlier work on this was due to Taylor, Burke, Kirkpatrick et al., and they modified the original Gillick and Favre ILP in order to incorporate this idea of compression. So remember that this idea was basically extracting a summary that has a very good set of bigrams, a set of bigrams that have high score under this, counting across different documents, or if you have some other kind of bigram model, you could use that as well. So they changed it so that now rather than extracting over sentences, they're extracting over nodes or sets of nodes in a parse tree. And so you have these two nodes here, S1 and S2, and you also need an additional constraint, which is that you should only include S2 if S1 is included as well. So fortunately, this can fit into this kind of integer linear framework because if S1 is 0, meaning it's not included, we say S2 has to be less than or equal to S1, and so then S2 is going to be 0 as well. And basically, this is just a kind of mathematical way of saying that including S1 is a prerequisite for including S2. Okay, so that's one type of thing that we might want to think about when doing this sort of compression, right? Like basically it identifies some things that we can delete that keep the sentence grammatical and then give the model the flexibility to delete them. But it's actually not the only thing we need to worry about, and it's not the only thing we need to worry about from the extraction point of view as well. So here's an example where maybe we don't care about this first sentence or about the president quitting. And then maybe we want to delete this, how much the new cereal plant would have cost. So we again can do that using parsing. But if we look at the summary that's left, the oat bran craze has cost it market share, and now Kellogg is canceling its new cereal plant. We're in a little bit of trouble here because we have this pronoun it, and we don't know what this refers to. In reality, it refers to Kellogg, and so what we should be able to do is we should be able to rewrite this pronoun and give us the summary: the oat bran craze has cost Kellogg market share, and now Kellogg is canceling its new cereal plant. That at least makes it clear what we're talking about from the first sentence of the summary here. So this was work that I did with folks at Berkeley during my PhD. And the basic idea was following on this prior work where we have a bunch of variables representing these different possible extraction choices, and we want to find the best set of extractions that maximize basically the score of the summary we'll get out. subject to constraints. And so the main new constraint that we introduced was this coherence constraint, that we have to basically make sure that we're going to understand what every entity mention reference is when we get there. So if we have a pronoun that doesn't have an antecedent that came before it, we better rewrite it in order to actually give us a sense of what basically of what that pronoun means. And so again, the grammaticality constraints here just enforce that you're cutting up your sentences in a grammatical way, and the coreference constraints, enforce this idea of sort of pronoun coherence. And one additional thing that we did was actually only allow the pronoun rewriting in cases where our prediction was confident. Otherwise, we just said, okay, we're going to do something a little bit weaker. We're going to force the previous sentence, or the kind of what we think is the antecedent of the pronoun, to be included in the summary. And this is kind of hedging the bets of like maybe the system made an incorrect prediction. So we're just going to ask for a little bit more context to be there as well. All right, in terms of how this works, so we have a couple of baselines. Well, we have a baseline from prior work and this lead baseline, taking the first N words of the document. And then we have a sentence extractive method. And so what we're looking at here is, on the y-axis, we have Rouge 1, so how good the summary is in terms of overlap with a reference. And on the bottom, we have linguistic quality. And so a sentence extractive method does pretty well on content, and the linguistic quality is only a little bit worse than the first N words, which should basically be perfect. So then if we extract just clauses, if we don't really impose strong syntactic constraints, we start doing really badly on linguistic quality, but better on content. And then our actual full system was able to, with all of these constraints, was able to basically keep the same linguistic quality as the sentence extraction, only a little bit worse, but again, better kind of content fidelity. And so in some more recent work, we and others have looked at these sort of compressive models and how to neuralize them. So basically this takes the same sorts of ideas but incorporates encoders like Elmo and BERT into them. And so we can encode both our sentence and also our possible compression option, and then treat it as a classification decision of whether we're going to keep the span that we're thinking about compressing or whether we're going to delete it. And so there were some other changes where we no longer formulate this as an ILP. Instead, we do beam search to basically pick up sentences and then decide what to do to them. But it overall works better than the earlier approaches. Obviously, leveraging these stronger pre-trained models in this framework is overall beneficial. So this gives you a sense of what's going on with compression. Essentially, it's typically grounded in syntax, although not always. And when we have some compression options, it's up to the model to decide, all right, how do you pick out the options which are going to convey the best content, respecting some constraints that we want to impose about grammaticality and coherence and things like that. That's the end of the segment.